session is on distance-sensitive hashing, and the talk will be given by Martin AuMuler.
Yeah, thank you very much for the introduction. So this is joint work with Tobias Cristiani, Rasmus Pei, and Francesco Silvestri. Francesco is also in the audience here. Maybe we can use that one. So, hello again. So this is joint work with Tobias Cristiani, Rasmus Pei, and Francesco. Francesco is in the audience. It's about distance-sensitive hashing. Distance-sensitive hashing came up as a result from studying some kind of recommender system problem, and that's so we run a large newspaper agency. We have this collection of all our newspaper articles. Let's say we are the New York Times. What we want to be able to do is recommend articles to users. So we know that a user read a certain article. What we want to do, we want to recommend some interesting other article to this user. And what is interesting, or our definition of interesting is very informal here, because we want something that is not too close to what the user read. It should also be not too far away. There should be some surprise in there. And such a system kind of runs on the New York Times website. Let's try to make this a bit more formal. So we try to embed this problem into an approximate similarity search problem. And in such a problem, we usually have some d-dimensional metric space X. And all of my examples are going to be on the plane for now, and it's 2 dimensions, it's very simple, but we should think about D as being 100 dimensions, 500 dimensions. It comes from some word embedding. So it's a very high dimensional space under some metric, say L1 norm or L2 norm, or if we talk about similarity, let's say cosine similarity is what we're interested in. What is this recommendation problem? If we want to formulate it, we coined it as the CR, approximate analysis problem. And it goes like this. So as the input, you get your data points, and you get these 2 numbers, C and R. What you're interested in is building a data structure that can solve the following problem. So you're given a query point, and you know that there exist points roughly at distance R. That's some assumption here. What you want the algorithm to be able to return is a point within this distance threshold, at least R over C, up to CR. So the C is some kind of approximation factor here. Okay, so all of these 7 points here that have this check mark, they are valid answers for our query, but we want to avoid returning close neighbors. We have to filter those out, and we want to avoid these far away neighbors. That's the problem. In very high dimensions, such a problem is usually difficult to solve. So if the problem is return the point that is closest to distance threshold R, then we probably can't do better than just linear scanning through the data set. We need linear time. If we have a large data set, this is going to scale very badly. By allowing for this approximation, there are other problems where all of a sudden you get sublinear algorithms, and using this concept of distance-sensitive hashing, we can solve this problem in sublinear time. And I'd like to discuss with you, like, how does our solution look like, and what is this distance-sensitive hashing? Okay, and for that, we first need to look at, like, how do hashing algorithms usually work. And so we have the same setting. We have our data set, we have our query point, and now in the most abstract way, what we are going to do in our application is that we are going to choose hash functions. We pick a random pair of hash functions, or we choose randomly from a family of hash functions, 2 functions h and g. And we are going to use h for all of our data points. And we just hash those to, let's say, a number, to some range. We are going to use this other hash function, g, to hash our query point. Okay, and I'll give you some examples for how these hash functions can look like. Now, how the algorithms then usually work, hashing-based algorithms, is, well, you hash down You look which of the data points collide with your query point. Those are the candidates, and you check these candidates through some exact distance computation. Do they actually have this property, for example, for the annulus problem, that they are at least a distance r over c, but at most a distance cr. As soon as you find such a candidate point, you return it, you're fine. Okay. What we are going to see a lot now is we are interested in collisions between query point and data points. So what we are really interested in for our hash family, how does this collision probability function look like that basically tells you what the probability is for points at a certain distance to collide. This is very abstract. Let's make this precise. So let's look at some hash families where we can pick such an H and such a G. And we are going to leave the Euclidean plane for now, and we are going to talk about bit strings. And so we talk about Hamming space, d-dimensional bit strings of length d. Our distance is very simple. We just count the number of positions where our bit strings, two bit strings differ. And to normalize that, we divide by this d over here to get a number between 0 and 1. And that is called the relative Hamming distance. There are 2 points that are going to be following us through this example here, x and y. X and y, they differ at 3 positions. They differ here, they differ over here, and they differ over here. So they differ at 3 positions, and they have 11 bits, so it's 3 over 11, that's the distance. Let's look about some hash functions, which we can apply to those 2 data points. And in 20 years ago, there was this breakthrough from Indig and Modwani where they proposed LSH. And LSH is one such family of hash functions. And what it does for bit strings is choosing a random function from a hash family means you choose some dimensions at random from your bit string. And the hash function says, I project down to those dimensions. Okay, so the underlined dimensions, that's what our random choice was. And then our hash code here is just projecting down. So that means that x has the hash value 0, 1, 1. J has 0, 1, 1 as well. H and G are exactly the same hash functions here. Okay. Now, if we look at the distance, so if 2 points have a certain distance, they differ in r positions, then the distance is r over d. If we want them to collide, then each of the dimension that we sample has to be one dimension where they don't differ, where they have the same input. Okay, so the probability that they collide, there's a fraction of 1 minus r over d points, and we sample k dimensions independently. So it's 1 minus r over d to the k. In particular, it's 1 minus distance to the k. And I just present this collision probability function here with respect to the relative Hamming distance. For 2 choices of k, 1 sample dimension and 3 sample dimensions. The important thing here is what can you do with a hash family that has such a collision probability function, and that's what Indig and Modwani basically recognized 20 years ago. Well, if you want to return points that are close to your query point, but you want to filter out those points that are far away, then this is a good hash family to do so, because points that are close are much more likely to collide. And actually, by increasing this number of dimensions, you increase the gap, a bit hard to see, between these collision probabilities. Okay, you can make it really unlikely to collide with a faraway point. That's the point of LSH. Okay, so applying this function into this LSH framework, which just wonders how many what are the points that collide with my query, that is going to solve this traditional near neighbor problem, where we are interested in returning a near neighbor. That's not the problem that we wanted to solve. Let's look at another hash function. So we have some choice here. So we have this H and this G. We can do whatever we want. Let's look at something we call anti-bit sampling, and that is just the original bit sampling approach, but for the query code, we flip all of the bits. Okay, so the query hash code is not going to be 0, 1, 1, but it's rather now 1, 0, 0. We flip all of them. now we can look at the same picture, but now it's like it's mirrored vertically. And without going into details, this could be very useful as a hash function if you're interested in having those points returned while filtering out closed points, because it's really unlikely that we are going to collide with a closed point. Okay, again, we can express this collision probability function down here easily as distance to decay in this time. It's some function of the distance. This is going to solve a problem like this, filtering out closed points while returning a point that is further away. Okay, we were interested in solving this annulus problem. Now I gave you two examples. I gave you an example where we were able to return closed points. I gave you an example where we were able to return faraway points. We are interested in those points here in the annulus. And the solution is just going to be we combine those two hash functions from before in a certain way. So what we do is we combine bit and anti-bit sampling. And here in the example, I say we sample our dimensions. The first dimension, we write over this original bit. For the remaining two dimensions, we flip the bit. Yeah, we do some bit sampling and some anti-bit sampling. The collision probability looks like this. It's, so if we sample k positions and flip the last L ones, then the collision probability is 1 minus the distance to the k minus L, that's the standard bit sampling, times distance to the L, that's the standard anti-bit sampling. The curve now looks like this. And if our parameters are, as shown here, I hope you all agree this would be a nice hash function if we want to filter out those points, filter out those points, but return a point that is roughly at distance r, because that one has a much higher collision probability. Okay, and that is like an introduction, and I hope you've seen now some ways to choose these hash functions. What is distance-sensitive hashing first, and then let's talk about how good is that solution for solving this annulus problem. So first of all, distance-sensitive hashing is exactly what we did with these three examples. So that's our definition here. So we have our metric space X, we have a distance measure, and we say that the distribution over pairs of hash functions H and G is called distance-sensitive with collision probability function F, which for each distance says what's the collision probability. If for each pair in our metric space we have that the collision probability of X and Y is exactly this function of the distance, yeah, that we would like it to have. And we saw such functions of the distance before. And in general, the message here is, if you know how the function looks like, then you might find a nice problem where, where hash functions like this are able to solve this problem for you. For example, if you're interested in near neighbors, then you really want to use some LSH, which is basically saying your function should be monotonically decreasing. If you're interested in filtering out near neighbors, then it should be monotonically increasing. If you want your an annulus query, then you need something that has a single peak. And this peak should be located within this distance. In our example, it should be located at distance r. Okay, and each function possibly gives you the opportunity to solve different problems here. How good was our solution for the bit sampling, of bit sampling and anti-bit sampling for solving these annulus queries? First of all, how can we measure that? Like, how can we say, like, now building a data structure from that, how good is this data structure going to be? How fast is it going to answer queries? The message here is you have to know this function, and you have to find out, you have to be able to analyze three function values. You have to look at what is f of r, what's the collision probability at r, what is it at r over c, what is it at cr. So that's f of r over c, f of cr. And then you plug it into this ratio of the logarithms over here. You get a rho minus value, which basically says that's how good you can filter out on the left. That's how good you can filter out near points. You get a rho plus value, that is just the value from an LSH. That is the filtering capability over here. with regard to how good you can return remain points over here. If you know rho plus and rho minus, the space of your data structure, if you just plug it into the standard LSH data structure, is going to be n to the 1 plus rho minus plus rho plus, query time n to the rho minus plus rho plus. That means rho minus plus rho plus here has to be smaller than 1. If it's smaller than 1, you win over a linear scan. If it's at least 1, then this doesn't have it all. The message here, the next message is this bit plus anti-bit bit sampling. That's unfortunately more of a pedagogical example. Yeah? So if you compute these, if you evaluate these functions, then you see the bit sampling part is fine. There's this rho plus with the approximation factor C that is known to be optimal for LSH. We do exactly the same. Unfortunately, the anti-bit sampling part is pretty bad. Yeah, when your distance gets very small and you basically have to distinguish close and very close points. Your behavior, this rho minus behaves like 1 over log C asymptotically. Now we plug these things in to the exponent and we get n to the 1 over log C. That's often smaller than 1, that's fine, but it's also exponentially worse than what we know from nearest neighbor queries on using LSH. Question is, can we do better? And for that we had to leave Hamming space. We were pretty sure there is a nice solution for Hamming space as well, but we couldn't analyze that one. What we did is we take our bit strings and transform them to unit length vectors on the unit sphere. This transformation, which just replaces these zeros by minus ones and scales everything by 1 over square root of d, has the property if the original distance was r over d here, it's going to be 2 times square root r over d here. So there's a nice correspondence between those two. And now, very shortly, what can we do on the unit sphere? We can use, there are much more powerful, there are very powerful constructions known. They go back to the papers of Becker et al., Cristiani and Andoni et al. From the last 2 years. What you do in these constructions is you have this magical threshold parameter t. That's what you read up from the theorems. The idea behind the algorithm is you sample a standard normal, d-dimensional standard normal. And then you say, with this standard normal, I associate a filter. And this filter is just a collection of data points. Those data points where the inner product with your random normal is at least t, this threshold value. Geometrically, this standard normal points into a random direction on the unit circle, and this being at least t means there is a certain threshold here. So it defines this kind of spherical cap over here. All the points that are on the surface of this cap, they are in the filter. And this is pretty good for finding near neighbors. If we just apply the same rule for our query points, yeah, then it's very good for finding these near neighbors. Now to get something that is really good at putting two near neighbors away from each other, you would turn this around, and in the picture you get something like this. Then you're interested in the query point should be, on the opposite side. Yeah, so this is the anti-bit sampling part here. And what we know, or what is known as this rho plus value for an LSF is 1 over c squared. This is as good as it can get. We show in the paper the anti-LSF also has this 1 over c squared. Question, is this optimal? Yeah. The annulus LSF is combining those two. So we get a 1 over c squared here, which in the original Hamming space, because the square root would be a 1 over c. So this is the answer. You can also do it in n to the 1 over c in Hamming space. Okay, are those constructions optimal? We really don't know with regard to this part. We don't know if you have to combine them in this way. This 1 over c squared, the order of 1 over c squared is going to be optimal, but the exact term is basically 2 times the rho value that we know. So this is unknown to us. What we show is this is optimal. Like this construction is as good as it can be. Okay, let's just skip over that. So what we show is if you are interested in returning a orthogonal vector while avoiding correlated vectors, then you can't do better than 1 over 2 c squared minus 1. And that's the LSH lower bound, but it goes in the other direction. It needs some other methods as well. Okay, and just to say, I mean, I won't have time to go through this. Distance-sensitive hashing is this concept, but it's not tied to solving annulus queries. Yeah, we also study another problem, which is privacy-preserving distance estimation. And there the problem is there's Alice and Bob. They have some user preferences. And what they want to know is, are they close to each other? But what they really don't want to say is, what is their preference in a certain sense? What they also don't want to know, allow is that the data structure to find that out leaks some information about the actual distance. Yeah, this is very important. Because in this paper over here, Riazi and others showed that once you leak the information about the distance, then you can actually triangulate and get closer and closer and closer to the original vector you were interested in. Okay, and we solve this problem where for an approximation factor C at least or greater than 1 and parameters epsilon and delta, we give an algorithm which says yes with good probability if they are close, and it says no, you're not close if the distance is above this, if the distance is above this distance threshold, which has this approximation factor in there. Okay, and that one needs some other step functions, and then some other annulus functions, and then it's basically each computes hash values, and they check in a privacy-preserving set intersection way whether there is a common hash element in their sets. Yeah, that's our solution, and but let's not go here into detail. There's also a poster session where you can ask about this application. So, what is distance-sensitive hashing? It's a generalization of this locality-sensitive hashing that captures many more collision probability functions. And my hope was to show you, and now there are other applications we can solve all of a sudden. Yeah? We can solve these annulus queries. We can estimate a function. That's something I didn't talk about, but if this collision probability function is something you're interested in estimating, but it's difficult, then you can just sample and estimate. And there's this privacy-preserving distance estimation. We've seen some initial constructions and this lower bound. What is open, I think, like from a practical point of view, the question is this useful? Yeah, is like this filtering capability of close points, is that something that you need in practice? Or is in practice not the solution using LSH and just looking at it and just finding in the LSH set which are the points that are furthest away here? Yeah, that could be another problem, solution to the annulus problem. We combine these annulus queries, we solve them by combining LSH and anti-LSH. And this gives you this n to the 2 row. And we have no idea how to prove a lower bound that this might be the solution here. We know it for the individual problem, but we don't know if we have to do this. And there is this which function f admits a distance-sensitive hash family. For LSH, that's a well-studied problem. Now there are a lot of new open questions here. Yeah, and that's it. Thank you very much for your attention.
Okay, so let me ask the most non-pods question I can think of, which is,
can't give an answer.
You know, well, so LSH is something that's found a lot of applications in practice. Yeah. So how far along are you in evaluating this? Do you have some proof of concept implementation, or?
I mean, we have concept implementations. We have and it's really simple to implement this because you take your favorite LSH implementation and you just replace this, how do you compute the hash code? Mm-hmm. Yeah, that's the nice thing about this distance-sensitive hashing. You can just reuse your favorite implementation. And then we can come up with adversary inputs where this greatly outperforms LSH for these annulus problems. Okay. Yeah, and but then if we actually want to do this recommendation task, our problem is we don't know how to evaluate it. Like, saying our approach is better than another one is very difficult. Yeah. So I'd like to have input on like how to evaluate these questions.
Okay. Yeah. Any other questions? If not, then thank you again.
Thank you so much.
That's it.